Today we are looking at a strange but very real idea in modern robotics. Delivery drones that can fly through the air, land on water, and then dive below the surface. This may sound unusual at first, but engineers are now building machines designed to move between air and water. These drones are not science fiction concepts. Several research teams and companies are testing real systems that can operate in both environments. The goal is simple: reach places that normal drones or boats cannot reach easily. In this video, we will walk through how these hybrid drones work, why engineers are building them, and what problems they may solve in the near future, from ocean research to rescue missions and remote deliveries. We will also look at the technical challenges behind them, because moving between air and water is not easy for a machine. The physics are very different, and the engineering solutions are surprisingly clever. Most drones today are designed for one environment only. They either fly through air or move underwater like small robotic submarines. Combining these two abilities into a single machine creates a new set of design problems. Air is light and offers little resistance. Water is dense and pushes back strongly against anything moving through it. A propeller designed for air does not perform well underwater, and a propeller built for water does not work efficiently in the air. Engineers solve this problem in different ways. Some hybrid drones use special propellers that can operate in both air and water. These propellers are designed to handle the sudden change in resistance when the drone moves from flying to diving. Another challenge is the transition itself. When a drone hits the water surface, the impact can destabilize the machine. Designers must control the angle and speed carefully so the drone enters the water smoothly. Some systems approach the water slowly and then sink beneath the surface. Others perform a controlled dive, where the drone intentionally pierces the surface and continues moving underwater. Once underwater, the drone behaves more like a submarine than an aircraft. It adjusts buoyancy, stabilizes its motion, and begins navigating through the water using onboard sensors. Communication is also difficult underwater. Radio signals that work well in air weaken quickly beneath the surface. Because of this, many underwater drones operate with partial autonomy. Instead of constant remote control, they follow pre-planned routes or react to sensor data collected during the mission. This allows them to continue working even when communication signals are weak. Battery design is another important factor. Flying consumes energy quickly, and moving underwater requires additional power to push against dense water resistance. Engineers often balance flight time and dive capability carefully. Some hybrid drones perform short underwater tasks before returning to the surface and taking off again. One major reason these drones are being developed is ocean research. Scientists often need to study coastal environments, coral reefs, and underwater ecosystems that are difficult to reach. A hybrid drone can fly to the location quickly, land on the water surface, dive down to collect images or sensor data, and then return to the air when the task is complete. This saves time and reduces the need for large research vessels, which are expensive to operate and require crews. Another possible use is search and rescue operations. When a vehicle sinks in water or a person disappears near a shoreline, responders must search both above and below the surface. A drone that can scan the area from the air and then investigate underwater may help rescue teams gather information faster. Military organizations are also interested in these systems. Hybrid drones could inspect underwater structures, monitor harbors, or explore areas where sending divers would be risky. Some companies are even studying how these drones could assist with underwater infrastructure inspection, such as pipelines, cables, and offshore installations. Some companies are even studying how these drones could assist with underwater infrastructure inspection, such as pipelines, cables, and offshore installations. Because the drone can fly to the site quickly, it reduces the time required to deploy underwater inspection equipment. However, building such a machine requires careful engineering choices. The drone body must be sealed to prevent water from entering sensitive electronics. Materials must resist corrosion from salt water, and internal systems must survive pressure changes when the drone dives below the surface. Navigation also becomes complex underwater. Satellite positioning signals cannot penetrate water effectively, so drones must rely on alternative systems such as inertial navigation or sonar mapping. These systems help the drone estimate its position while submerged, allowing it to complete tasks without constant GPS updates. Another engineering concern is stability when leaving the water. After completing an underwater mission, the drone must rise to the surface and transition back into flight mode. If the motors start too quickly or unevenly, the drone may lose balance during takeoff. Designers solve this by carefully controlling thrust and orientation before liftoff. Some prototypes slowly rise from the water surface before increasing thrust and climbing into the air. This controlled transition reduces mechanical stress on the drone frame. Even with these solutions, hybrid drones remain an active area of research. Engineers are still testing different shapes, propulsion systems, and navigation strategies. Small improvements in efficiency or stability can greatly increase how useful these drones become in real-world missions. As technology improves, we may see hybrid drones supporting marine science, environmental monitoring, disaster response, and infrastructure maintenance. They represent an interesting step toward machines that move freely between very different environments. Hybrid air and underwater drones show how creative engineering can solve unusual problems. By combining aircraft and submarine design ideas, engineers are expanding where robots can travel. These machines are still evolving, but the early prototypes already demonstrate that crossing the boundary between air and water is possible with the right design choices. In the coming years, we will likely see more systems that operate across multiple environments, not just air or water alone, but combinations of land, sea, and sky. And as robotics continues to develop, these hybrid machines may quietly become valuable tools for science, safety, and exploration. For now, they remain a fascinating example of how far modern engineering is willing to go in order to reach places humans cannot easily reach. Thank you for spending this time with us here on Forgexa, and I am your host, Sam, where we explore practical technology, engineering ideas, and the systems quietly shaping the future. If you enjoy clear explanations of emerging machines and real-world innovation, you are always welcome to return for more conversations like this. Until next time, this is Sam from Forgexa. Thank you for listening.